this lesson, you will understand the concept of supervised learning, regression and classification. By the end of this lesson, you will be able to list the different types of supervised learning, outline the various regression algorithms, illustrate the advanced regularization techniques, analyze logistic regression and accuracy matrix, build various regression models, illustrate classification as part of supervised learning, evaluate classification models, demonstrate different classification techniques in Python. Supervised learning.
Supervised learning is a type of machine learning used to train models from labeled training data. It allows you to predict output for future or unseen data. So what is labeled data? Labeled data is a group of samples or features that are tagged with one or more labels. Training data needs to be fed to a machine learning algorithm in order for it to generate a machine learning model that learns from your algorithm. The learning algorithm discovers patterns in the training data such that the input parameters correspond to the target. The output of the training process is a machine learning model which you can then use to make predictions. This process is also called learning. Let's understand supervised learning by looking at some examples. Consider the weather app. It makes predictions based on prior knowledge and analysis of weather over a period of time for a particular place. Weather forecasts are created by assembling as much data as possible concerning the present state of the atmosphere, particularly the temperature, humidity, and wind, and understanding of atmospheric process through meteorology to determine how the atmosphere will evolve in the future. Supervised learning can be used in this case as all data is labeled data. Let's look at another example. We use Gmail filters every day. Gmail filters are used to decide whether a new email has to fall into the inbox, normal, or junk folder spam based on past information of spam. Whenever a new email comes in, Gmail checks for spam based on the sender's email, IP address, and email content. If Gmail finds any of these misleading, it flags the email as spam. It also collects further reactions of the email receiver. Has the user marked an email in the spam folder as not spam or opened the mail? Similarly, if an email is marked as not spam, does the user mark it as spam or delete the email immediately, or does the receiver block the sender? Supervised learning can be used in this case, as all the data is labeled data.
Supervised learning. Real-life scenario.
Have you ever wondered how Netflix makes recommendations? When you first sign up, it asks you to choose the 3 shows you like, and based on that, it predicts more shows that you like. Let's understand how it uses supervised learning to do that. Netflix uses supervised learning algorithms to recommend shows to you based on the genres you choose and ratings by similar classes of users. Similar classes of users are those who selected the same shows you did when they first signed up. When a new user finishes signing up, the user is given recommendations by algorithms trained on historical data. Historical data can be the most watched shows by new users in the past, most searched shows by a new user in the past, or other relevant information.
Understanding the algorithm.
Now let's understand the algorithm behind the learning model. The training data consists of inputs, also known as features, and output, also known as labels. For example, the color, size, and weight are the features of a fruit, and the name will be its label. Consider the given training data. X column is the input, and Y column is the output. Train the algorithm by applying reverse engineering by looking at the relationship between X and Y. What is the relationship that has been defined here? Y equals F times the set of X, where Y is some function of X. This is also called as learned algorithm. Using the learned algorithm, predict Y values for the new instance using Y equals F times the set of X.
Supervised learning flow.
Let's understand the flow of supervised learning. There are 2 steps involved in building a supervised learning algorithm. The first step is training and testing. The second step is prediction based on training and testing. Let's understand the training and testing phase. Once you have gathered all the historical data, you need to do the random sampling of the gathered data. This will give you the train and test data set, which is divided in the ratio of 70 to 30. What is random sampling? In random sampling, the total population data is randomly distributed between different samples, where each sample has an equal probability of being chosen. A sample chosen randomly is meant to represent the total population. If the sample does not represent the total population, apply machine learning algorithm on the trained data set, that is 70% of the sample data, and use statistical modeling. You will get the predicted value as the result of it. The test data set, the remaining 30%, is used to validate the predicted outcome and come up with the model validation outcome. Now, when you have tested the data, you may want to use to make predictions and gain insights. So, let us understand prediction. Once you get the model validated outcome from the training and testing phase, use that as a new data for prediction. Apply statistical modeling and use the learned algorithm y equals f times the set of x to make predictions. You will get the prediction outcome as the output from the statistical model. Algorithm prediction can be improved by more training data, capacity, or algorithm design.
Types of supervised learning. Part A.
There are two types of supervised learning: classification and regression. Classification is a supervised learning type where the output has predefined labels that have discrete values. A discrete value is a value that is obtained by counting. The goal of using classification is to predict discrete values belonging to a particular class and evaluating on the basis of accuracy. Regression is a supervised learning type where output is a continuous value. A continuous value is a value not restricted to defined separate values, but can occupy any value over a continuous range. The use of regression is to predict a value as close to the actual output value as our model can, and then evaluating it by calculating error value. The error value is inversely proportional to the accuracy of our regression model. The smaller the error value, the greater the accuracy to the regression model. In supervised learning, the algorithm is selected based on the target variable.
When can you use classification? You use classification when the target variable is categorical. In other words, classification is applied when the output has finite and discrete values.
Let's understand it by using an example. Suppose you want to predict the class or category of a car when you have its feature details with you, like horsepower, mileage, weight, color, etc. The classifier will build its attributes based on these features, and the analysis has three potential outcomes: sedan, SUV, and hatchback. So here in this example, you have all the categorical data with you, and thus it becomes easy to predict outcome using classification.
Types of supervised learning. Part B.
Let's try to understand classification and regression by looking at the given graphs. We will cover classification first. Classification either predicts categorical class labels or classifies information that is used in the classification of characteristics to build a model based on the training set and values. As shown in classification graph, the red diagonal line is also called as classifier, and the points above and below the line are two classes. In each class, the distance from the newest point to the red line is the error of classification. Regression graph involves finding the best fit straight line through the plotted points. The best fit line is called a regression line. The red diagonal line in regression graph is the regression line and consists of the predicted score on y for each possible value of x. The error of prediction for each point is the distance of that point from the regression line. The point that is very near to the red line has small error of prediction and vice versa for the point that is far from that line. Now let us understand when you can use regression. You can use regression when the target variable is a continuous numeric variable, such as numbers from 100 to 2000. Or in other words, regression analysis is used when you want to predict a continuous dependent variable from a number of independent variables. Let's try to understand it through an example. Assume you want to predict the price of a house, given its features like square area, location, number of bedrooms, etc. Here the price is a continuous numeric variable that can be predicted using a simple regression algorithm. Use the equation y equals w times x plus b. This equation shows the relationship between price, y, and square area, x, where price is a number from a defined range. It is used to estimate discrete values, for example, binary values like 0 or 1, yes or no, and true or false based on the given set of independent variables. Decision tree. It makes sequential hierarchical decisions about the outcome variable based on the predictor data. Random forest. It is an ensemble of decision trees. It gives better prediction and accuracy than decision tree. Naive Bayes classifier. It is on Bayes' theorem and works with assumption that features are independent. Support vector machines, SVM, draws hyperplane in a feature space that separates instances into different categories with margins in between as far apart as possible.
Types of regression algorithms. Part A.
We will focus on 6 types of regression algorithms: linear regression, multilinear regression, polynomial regression, ridge regression, lasso regression, elastic net regression. Let's look at these regression algorithms in detail. So what is linear regression? Linear regression is used for finding a linear relationship between the target and one or more predictors. It is a statistical model used to predict the relationship between independent and dependent variables denoted by x and y respectively. Let's try to understand this by examining 2 factors. The first factor is how closely x and y are related to each other. The result of linear regression is a number that falls between -1 to 1, and it indicates the strength of correlation between the 2 variables, x and y. 0 indicates no correlation. 1 indicates positive correlation. -1 indicates negative correlation. The second factor is prediction. When you get the result of linear regression that also represents the relationship between x and y, use that result to predict the future value of y for a value of x. This is done by fitting a regression line and is represented by a linear equation, that is, y equals a times x plus b. You can predict scores on one variable, that is y, from the scores on a second variable, that is x. The variable you are predicting is called the criterion variable. The variable you are basing your predictions on is called the predictor variable. What is multilinear regression? The multiple linear regression explains the relationship between 2 or more independent variables that are x1, x2, x3, etc., and one continuous dependent variable that is y. It is a statistical technique used to predict the outcome of a response variable through several explanatory variables and models, the relationships between them. Equation for multilinear regression is y equals m1 times x1 plus m2 times x2 plus m3 times x3 plus so on plus mn times xn plus c, where y is the dependent variable, m1, m2, m3 till mn is the slope and c is the coefficient. Let's move on to polynomial regression. Polynomial regression is a form of regression analysis in which the relationship between the dependent variable y and the independent variable x is modeled as an nth degree polynomial in x. It is applied when data is not formed in a straight line and is used to fit a linear model to nonlinear data by creating new features from powers of nonlinear features. Look at the given example. Here, y is modeled as the square degree of polynomial in x.
Regression use case.
Let's look at a use case of regression. Suppose you are running a company and you want to predict the profit of your company in the coming months. This can be done using regression analysis of profit estimation depending on the expenditure of the company.
There are multiple departments that have their separate budget of expenditure, such as research and development, administration, marketing, sales, and profit. So, by using multilinear regression, you can predict the profit estimation of the company. Accuracy metrics.
Now that you know how to use a regression model to make a prediction, you can validate your prediction using accuracy metrics. R-squared is the most common metric to judge the performance of regression models. Its value lies between 0 and 100%. The equation of R-squared is represented here, where Y actual is the actual outcome value, Y predicted is the predicted value of Y, and Y mean is the average value of Y. If you apply R-squared on your linear regression model and you get the value 16, it means you have 16% of the information you need to make an accurate prediction about the price. The disadvantage with R-squared is that it assumes every independent variable in the model explains variations in the dependent variable. This can be solved using adjusted R-squared. This is a modified version of R-squared that has been adjusted for the number of predictors in the model. The equation for adjusted R-squared is shown here, where R-squared is R-squared value, P is the number of predictor variables, and N is the number of data points. It is recommended that you use adjusted R-squared when working on a multiple linear regression.
Cost function.
Let us understand mean squared error, MSE, first. MSE can be used to measure the performance of a model, and a root mean squared error, RMSE, is just the square root of the mean squared error. It is the distance on average of a data point from the fitted line measured along a vertical line. The equation related to MSE and RMSE is shown here. Where N in the equation is the number of data points, YI is the predicted value by the model, and YI underscore is the actual value for the data point. These functions are called the loss function or cost function. Cost function is a value that has to be minimized. In the next screen, we'll discuss how to use gradient descent to reduce the loss function. Gradient descent is a first-order iterative optimization algorithm for finding the minimum of a function. It tweaks its parameters or coefficient iteratively to minimize a given cost function. The model stops learning when the gradient or slope is 0. Gradient descent algorithm has 2 steps involved. The first step is to initialize the parameter by some value. The second step is to calculate the derivative of the cost function for each iteration and to simultaneously update the parameters. The equation for gradient descent is, where A is the learning rate that controls the size of adjustment. It must not be too small, else the learning will take very long, and must not be too large, else the network will not get good coverage. And theta is the matrix value.